Yeah, I guess we can get started. Welcome back, everyone. Kind of a light class, not as light as my first class for the day, so I appreciate you all making it in, especially the folks who made it in on the Zoom side. It's weird to have an in-person slash online class with no one on the online side coming in. But welcome back, folks, for the announcements. Major thing I wanted to probably remind myself is that exam two grading is going to start pretty much on Friday, but I give an exam in all my classes, so it's going to be a heavy grading weekend for me. It'll occur over the weekend, the grading of exam two, and probably it's going to finish sometime around Sunday for this class. So it'll take a bit, but we'll get through it. I need to start grading the homework sets first because I like to let you know where your grade standing is after grading of exam two. And then once exam two is graded, I'll start emailing them back if you took them in a testing center. If you took the exam two in person, and if you'd like to have it before coming back from spring break, just send me an email. I'm checking my email each day in the morning, and I'd be happy to scan your exam and send it right to you. So the exam is not quite yet graded. It hasn't begun. I'm still waiting to get the exams sent to me back from the Pocatello Testing Center, or maybe I should check my emails. I might have gotten them back already. But for what we're doing today, we're just moving forward through chapter 18. We looked into this briefly and derived the theorem, the new central limit theorem for the difference in means. And now we are ready to restart our methods, doing confidence intervals and hypothesis test. So that's what chapter 18 is all about. And when we return from the break, after this is finished, if we don't finish today, we're making a big change in our methods. So far, you might have noticed in chapters 14, 15, 17, and 18, all the data has been quantitative. We're going to start changing gears, looking to categorical data, starting with categorical data with specifically two outcomes, and then working from there. It'll mirror quite a bit what we did in chapter 17 and chapter 18, and then it goes a little bit beyond that even. So that's where we're at so far, folks. Any questions or comments at the moment? Okay, well, let's get started then. Here's where we left off directly a week ago from today, right before dealing with the exam. We just looked into some central limit theorem information, and going up on the notes, it was a step-by-step derivation to get to this point right here. The sampling distribution of the difference of two independent sample means, x bar 1 minus x bar 2, is distributed as this normal distribution. Because it's a central limit theorem, the same ordinary comments would apply that, for example, this is an approximate distribution. That's important to know. But what makes it a great theorem is that not that it's approximate, it's how the approximation improves. This approximation right here, where we say is distributed as normally, gets better and better as the sample sizes, both of them, increase. So we'll say as n1 and at the same time n2, both sample size have to increase, not necessarily at the same rate, but they have to go up. As n1 and n2 get larger, the approximation gets better. There's a lot to say about that altogether, but what we mean by gets better, by how much larger do n1 and n2 have to get? But we'll encapsulate that kind of information when we look into the robustness conditions for our new methods in this chapter. And if you're interested in more detail on how that works, good course on probability and calculus with limits is what's really about. It's really a limit statement in probability, what that's going on here. So major thing we wanted after we got that derivation to go through was we took this. This is a big challenge for us, even when we were in, say, chapter 17, because our confidence interval looks like this. X bar plus or minus a T star times, well, we used to have sigma over root n right there, but now we put in a standard error of X bar, where that value was S over root n. So we went to this location, essential limit theorem in chapter 17, and just put in S. But now that we have two sample means we're considering simultaneously, the standard error this time is found from coming up here In the brand new central limit theorem, we make two adjustments. Where there was a sigma 1 squared and where there was a sigma 2 squared, put in S1 squared, S2 squared. That's informed as being the correct move by those estimates right over here. And that's our new standard error that we use in this location for our new methods. So now we'll say in chapter 18, we're doing x bar 1 minus x bar 2 plus or minus a critical number t star like before. Oh, give me a moment. I need to constantly remind myself that this document doesn't like the pencil tool for some reason. It usually comes back though, so we have like this weird mental break while Microsoft Word is thinking about it. Let's see if it's going to work. Oh, it's not even trying. I don't see Microsoft Word on here on the list whatsoever. I think I upset it more by clicking on it. Well, let's just see if we can crash it out and come right back in. Sorry for that distraction, folks. Maybe a restart will work on this. I heard we're getting more powerful computers because of a mandatory update to Windows 11. So hopefully next academic year, this will be a less of an issue. Let's see how much stuff saved. Nothing at all. That's kind of unfortunate. Only reintroduce those comments later on after class. Let me put in a reminder. Include comments about central limit theorem effectiveness, that it gets a better and better approximation as the sample size gets larger and larger. But I don't know if it's a great use of class time just to watch me retype out those or write out those comments. So let's say what we were just doing down below here, but maybe in a more stable way. Once we have this standard error, our new method is x bar 1 minus x bar 2. We're taking that difference because the point of our confidence interval is to estimate a difference in population parameters we'd call mu1 minus mu2. And this takes us all the way back to the very first day of class. X bar 1 minus X bar 2 is already an estimate, and it's a good one. When the sample sizes get large, it gets even better as an estimate of mu1 minus mu2. So what's wrong with this? There is nothing encapsulating the margin of error or the reliability of the estimate. So that's why we have to do all this hard work of going add and subtract a critical number t star, which comes from a very abstract probability distribution related to the normal one. Then we have to add in a new structure, standard error x bar 1 minus x bar 2, which comes from an even more abstract thought. The central limit theorem is telling us that this difference in means is coming from a whole new population distributed just about normally. Put that all together, and that's our brand new confidence interval. This is the one in chapter 18. And just comparing our methods, look at the parallelism here. It's kind of great in a way. In chapter 17, we just took x bar because we're estimating just one mean. Let me add just an additional thought here for parallelism. To estimate just mu, we took the sample mean x bar, added and subtracted t star, multiply it by the standard error of just x bar itself, and that did the job. So now, even though we have two parameters, two independent populations, and it feels like there's a lot more abstraction, really the bigger thing that happened was the formula for standard error got more involved. And one other thing we'll take a look into. But it's kind of nice to see there's huge parallelism in how we construct the interval. And it feels very, very similar when we go to interpret that interval. We just make an interpretation that our estimate of mu1 minus mu2 is that it lies between whatever two numbers that are provided here. We have to say all that stuff with context, but it's nice to know not big of a difference from what we did prior. So we'll scroll down, take a look into the methods. Any questions first? Okay, here's our brand new methods then. So we'd call these the two sample t procedures. Lots to discuss here, so let's go through these elements one at a time. This is the confidence interval we were looking at, contrasting it with the chapter 17 interval. The whole purpose of this is to estimate mu1 minus mu2. But because this is the two sample procedures, we have to also think about why do we use this method? It's because we have a simple random sample, size n1, the unknown population mean mu1, and we took a second independent simple random sample. Let's maybe highlight this part. Different sample size with another population with a different parameter, mu2. But it's all about that statement right here. Independence means whatever measurements we get from our first sample of N1 observations don't influence in any way the measurements in the second sample of observations. Dealing with humans, dealing with contagion, that kind of stuff can violate independence in a really easy way, unless we're just very mindful for how the study was conducted in the first place. Reading a study with two sample procedures usually has a big section on how they gathered the data, their randomization, a big section on how they believe independence is the result of their sampling design. And so these are kinds of the things that are addressed quite a lot when you're conducting and carrying out the study. Puts us in a really weird spot because we're just looking at the statistical methods themselves. So we're jumping to the analysis of the data when you already have it. We just have to remind ourselves it had better come from independent samples. Now, pause on that thought right there. In chapter 17, we did a problem that almost looks like it fits, but it doesn't. It was this one, thinking about stress. We had two samples, a sample of measurement at 12 hours before an important surgery, another sample of measurements 10 minutes before that important surgery. It was two samples, but these were absolutely paired and dependent data because the measurement at 12 hours in some way absolutely does affect the measurement at 10 minutes because this is the baseline measurement. Stress goes up and it's influenced by where you were at the baseline. A patient is measured twice in that way, in other words, that's automatically dependent data. So that's what's the difference here when we're talking about independent. We can't have a study like that going on, no paired data whatsoever. We would have to draw one sample of people, 19 people at the 12-hour mark, a whole different sample of new people at the 10-minute mark. It would be a doubly expensive study, for example. So that's why we would use these methods here. T-star is the same kind of critical number that we looked into calculating in chapter 17. So the methods are almost the same. Here's the one big difference though. When you go to calculate T-star, you're using the degrees of freedom DF. And the degrees of freedom DF are given by this unsavory looking formula down here. It's kind of strange. One thing we never discussed about in chapter 17, because it just wasn't relevant at the time, was that the degrees of freedom for the T distribution does not have to be an integer. It doesn't have to be 6, 7, 8, 9. It can be 9.2783, for example, and it's a valid T distribution for any real number. Pretty weird. So we use these degrees of freedom right here to come up with the critical number T star, plug it back in. That does the confidence interval for us. If it's a hypothesis test, we still calculate degrees of freedom, throw the standard error down the denominator, and that's our test statistic, just x bar 1 minus x bar 2. That's kind of nice in a way. Notice there's no minus mu naught or something along those lines. That's what we would have had in the chapter 1 method. There's no minus mu naught sub 1 minus mu, that's hard to type. Let me try again. Minus mu naught sub 2. We could put them in there, but there's a really good reason why this is just gone from the test statistic. When we go to use this method, our natural null hypothesis is going to look like this. H naught, mu1 equals mu2, or an equivalent way to write this is H naught, mu1 minus mu2 equals 0. There's really a -0 here because our assumption in the null hypothesis is that the populations are the same with respect to the parameter mu1, mu2. It's really the same parameter is what we're saying, or the difference between the two is 0 itself. So we don't need to put in any value right here. This is what our null hypothesis will look like for all the problems in this chapter. So degrees of freedom we'll calculate by hand to get a feel for it. I did do a simplification here. I felt like this S1 squared divided by N1 plus S2 squared divided by N2 is just too similar to that. So you could simplify the formula by, say, if you square this, the root comes off. If you raise it to power 4, you get power 2 like you see right here. You would have already calculated the standard error if you're doing a confidence interval or a hypothesis test. It goes in the denominator there. So if you already have the standard error, I would say this is the most logical way to compute it. Use what you've already computed, raise it to the 4th power, and now you're mostly just worried about what the denominator looks like in this formula. And even though it looks kind of nasty and convoluted, easier to memorize than you to believe because numerator is just your standard error to a 4th power. And what about the denominator? Think of it in terms of chunks. In this first chunk, we take 1 divided by the sample size from the first population reduced by 1, S1 squared divided by N1 squared. And then the second term is the same. You just move the subscript over by 1. It's sample 2, so N2, here, S2, here, same exact structure. So if you think in those kinds of terms, not too bad of a formula to memorize. Not that you have to memorize all the formulas in this class, but the more you can kind of get into your head, the easier they are to use when we have to use them on an exam setting. This would be a supplied formula because I don't know if that's a good one to leave off. So that describes our full methods. Any questions at the moment, folks? Okay. Other good news is that if you're doing a hypothesis test, we call that the two-sample t-test. The null hypothesis can be expressed in 2 ways. Here, that's the second option, exhibiting 0, also mentioned here. Or you can just say mu1 equals mu2, would be completely equivalent. And for the tests, we calculate the p-values in the same exact way. So whatever your test statistic comes out at, take a look at the guidance in chapter 17. We have a nice table there. It describes all the syntax. So really no change at all in calculating the p-value. So with all this, I think we're ready to start a brand new problem, example 3. Example 3 is written in a way where this one would look like an exam 3 question. Notice it's kind of like a guided tour on things to calculate. The problem down below, this one's written in more of this way as a homework question where you're doing the full analysis, including the discussion on condition checking. That's where it takes quite a lot of time to get through. So let's start off our problem by, just as a quick reminder, this is a written in a style similar to an exam 3 question. Just keep in mind what I really mean by that is certain things like calculate the critical number, I would have to pre-compute on the exam. You're just doing the major concept of putting the information together and then giving an interpretation. Okay, so let's start in earnest. This is a pharmacological study. They're measuring the concentration of the brain chemical dopamine in 6 rats exposed to toluene. So this will be the treatment group. Toluene is an interesting chemical. This is a study from the 80s, and I think this is motivated by, back in the 80s, a lot of people were abusing inhalants, and there was a lot of public service announcements about it. That was one of the bad chemicals and a lot of different things people were inhaling. So that's probably what the study was really all about when it was conducted. So 6 rats exposed to a pretty nasty chemical, 6 rats in a control group. We should assume that these rats were randomly assigned to both groups because this was published in a toxicology journal. Only way to know that for sure, though, is to read the study. You never have to do that in this class. I'd say it's probably a safe assumption that this was a real, randomized, well-controlled experimental design. We have a control group, a toluene group, And the rats should have been randomly assigned to both of those groups. It now tells us the summary statistics for concentration of dopamine, this is in nanograms per gram, in the striatum region of the brain, are provided in the table below. So here's the study if you're interested in it. We have our table down below. It's formatted in a way that is kind of confusing, so we need to be careful with it. So we have two groups totally in control, the means and standard deviations. But you know what's also missing in this table is the sample sizes. Let's write that in. So we'll say, how should we say this? Maybe N1. This would say first sample is 6. Toluene. I really don't know how to pronounce that. So correct me if I'm wrong, if you do know and it's bothering you, my mispronunciation. So the toluene group has 6 rats. The control group has N2 equals 6 rats. And notice I did make a choice here. It might make more sense to you to call this NT, sample size for the toluene group, and C, sample size for the control group. Some people prefer just N1, N2. So I'll try to use both methods. On the next problem, I'll use a little bit more of a better description on these. On this one, I'll keep it generic, N1, N2. We have a practical question over here. Is there evidence that the exposure to toluene causes an increase in dopamine levels in rats? Seems to be more about, again, the drug abuse going on in the 80s. This was done to spike your dopamine. That seems to be like it was what it was all about. So they're checking it in the rats themselves. These are those dopamine levels. The toluene group is at 2,500, and the control group is at 1,800. So we're wondering, is that statistical significance for a difference? Standard deviation is also important, but we made a comment about the test we're running. We're running a test called the Welsh two-sample test for either the confidence interval or the hypothesis test. It doesn't assume equal invariance. It allows for unequal ones, which is great. We don't have to worry about, are these too far apart to be considered unequal? We'll allow them to be unequal and still give a very robust analysis to these same data. First, we have to say, what are we even estimating? So now we're back to the hard topics, same kind of topic that we were dealing with on the very first day in class. It says unknown parameters, but by this, what we really mean are the parameters we're setting out to actually estimate. So let's start by saying, for this right here, let mu1 and mu2 denote the population mean it's going to be the mean value for whatever this stuff was, but we were told that this is, let's see here, concentrations of dopamine with that unit in the striatum region of the brain. We can make this a little bit paraphrased. You don't have to say average concentration of dopamine in the striatum region of the brain. We can just say more tersely, population mean dopamine concentration in nanograms per gram. I would say the unit is definitely important. That's a weird way to say gram, GM. I usually write it as G. For people who are experts on units, does that mean grams or am I missing something on that unit there? Weird. Let's take a quick look here. Is GM a way to denote grams? Okay, looks like it is. So we'll go with that. Looks like we are dealing with grams in that. It's just good to know for certain. So we'll say here, we're not saying the striatum region of the brain. We'll let the firm context up here capture that. But we have to also capture that there are two populations, the toluene population, the control population. We define those means. So let's say here, we have the population mean dopamine concentration for the toluene group and the control group, respectively. We've talked about this word a little bit before. It's kind of my favorite word if you have to indicate multiple means. When we're in ANOVA sections, we might indicate 3, 4, 5 means at the same exact time. So that word becomes really important. For people who've taken loads of math, this defines a real mathematical one-to-one correspondence, where mu1, the thing that came first, is now referring to the talling. Mu2, the thing that came second, is referring to control. Because we said respectively, we're respecting the order that we indicated the objects in the sentence. Just saves you lots of time in writing, so it's a cool way to indicate information. I'll make use of that quite a lot, so I feel like I have to explain it at least once. I think this is the second time, but no harm done. After we have that down, we know what we're estimating, and the next thing to go for is standard error. Any questions at the moment, folks, with what we've got down? Okay, so standard error for the difference in sample means, all of this would be called SE. This is how our author typically defines these objects when you look into the reading, just SE, and you have to use the context to tell you which SE formula we're using. In my notes, I attached this extra thing, making SE more of a function that takes the statistic or the combination of statistics you're approximating. When it says difference in sample means, it's a standard error for X bar 1 minus X bar 2. Now, X bar 1 is referring to this value, X bar 2 is referring to that value, but that's not what we're actually calculating. This is just a structure that says we're computing this formula. It's S1 squared over N1 plus S2 squared over N2. This is the same formula that we derived at the top of the notes. So now let's go to the standard deviations down here on the table. For the toluene, that's S1, 565.19. For control, S2, that's 411.84. So back down here, we just import that information. Square root of 565.19 squared. Divide by sample size N1, that one is a 6. Plus S2 squared, that's 411.84. Squared, divide by 6 again. One comment we'll make is we're usually pretty happy when we have equal sample sizes in this specific context, 2 independent samples, because it means the power behind our procedures has gone way up. And more importantly, the robustness of our procedures has gone way up as well. It means if we were doing condition checking on this, that's really nice. But keep in mind, it also means if this happens, that's not a severe punishment. It doesn't mean the conditions are not met. It's just not ideal. But sometimes things happen. A rat could have just inexplicably gone missing and no one can find it. And we just work with the data that's left. So these things happen. It's probably why in this problem, there are only 19 patients. Something might have happened. Maybe a surgery was canceled. Maybe the surgeon, him or herself, canceled on that surgery. Couldn't include the 20th patient. So those things happen. Here, it's a bigger deal if we unequal our sample sizes, but it won't stop the procedure. It just makes everything less robust. But now finally down here, we grab a calculator. Any calculator whatsoever will do the job. Again, imagine we're doing this one as an exam 3 problem. We would type in our calculator, square root 565.19 squared divided by 6, plus, for this part, 411.84 squared divided by 6. Order of operations look concerning here, but with the power, the division happens after the exponentiation, so we don't need excessive parentheses. And this is the correct standard error. Let's keep 4 decimal places, 285.4972. And these are easy to make a mistake on. Honestly, why the reason I keep bringing up, show what is going in the calculator on paper before you put it on the calculator for exams, is because, well, the degrees of freedom is even worse. These are easy things to kind of make simple mistakes. Even when you're really great at the calculator, you're in an exam setting, so your thumb could slip, for example. So if you've got a totally different figure, but this is on paper. In an exam setting, you might not even lose any points at all, maybe a half a point at worst. But any questions at all, folks, with getting the standard error down? Okay, here's the next part. It's a little bit rougher, but it's just like part B. You write down the formula. The fifth official mathematical technique after that is just plug and chug. Just import the information you have, crank it out. So degrees of freedom here. First, I want to make a really short comment. If this was one sample, degrees of freedom would be 5, just one less, right? If we assumed equal variances, this is total sample size of 12, degrees of freedom would be 10. Here, we're not going to get 10. Variances are a little bit unequal right here, but we might get something pretty close. If I got degrees of freedom around 1, I'd be really concerned. But if I got degrees of freedom close to 10, it'll tell me it was maybe a little bit close to being equal variance, but just a slightly off. Anything lower than 10 by a significant amount means variances were becoming quite unequal. That means degrees of freedom is dropping, t-distribution is getting wider in its tails, making your confidence intervals wider, making your p-values larger. So that's what's going on with this degrees of freedom right here. It's allowing for the unequalness and the variances. What we do is we take standard error just calculated, raise that object to the 4th power. Then there's a weird structure in the denominator, but here's how it goes. You take sample size minus 1. That would be N1, first group, minus 1. Then you take the standard deviation for first group, square it, divide by the first sample size, square that again. Kind of weird. But once you get that down, just repeat the whole structure. You're just changing the subscript. Plus 1 over N2 minus 1. S2 squared divided by N2 squared. So that's the whole statement right there. On the next line, we're going to start calculating this. So first import the standard error, 285.4972. That's raised to power 4 in the numerator. And then looking to our sample sizes, it tells us this will be a fifth and this will be a fifth, which means you could have just factored out a fifth and simplified the formula. The reason there's no formula simplification really is it's designed specifically to allow for unequal sample sizes. Sure, we want equal sample sizes, but the reality is we don't always get what we want when we conclude a study. Things happen, in other words. So this one is just 1/5. S1 is this quantity, but we have to also square it now. 565.19. Divide by N1, which is the full sample size. So you should always see a denominator 1 less than the one to the right when you go to write this out. That's a bit of error checking just by visual inspection. Then we do it again, 1/5. Take the other standard deviation, 411.84. Square it inside the fraction, divide by 6, and square that fraction as well. If you've got that on paper, this is a situation I would give you full credit, even if you did make a mistake in the calculator. There's a lot to import. This is stuff that we do pretty well when we're not stressed out, we have the time in a homework problem setting. But if you've got this on paper, I'm happy. This would be full credit in an exam setting. You should still calculate it because if it comes out negative, you'd know there's a mistake in one of those numbers. So that would just be for extra confirmation. So this is what we'll do. 285.4972 power 4. Let me know if you detect any mistakes in my typing of this. So that takes care of the numerator. Denominator's right here, and that first parenthesis is to capture the whole denominator. I want another parenthesis for 1/5, just to be careful. Probably I didn't need that by order of operations the way it interprets it. You need to put in a literal multiplication if you're using R to do this computation. Then go to the next fraction, 565.19 squared, divide by 6. Square that fraction, and that's the first group. We just need to do it one more time. So here's another 1/5 times next group, 411.84 squared divided by 6. Square that one. And this is a good point to just sort of pause and reflect. Did it really type in right? Let's take a look. Something to power 4 in the numerator. A fifth, 565.19 squared is that part. Divide by 6, square the whole fraction. It looks like the same pattern to the right, the same numbers. I'm pretty convinced, so let's see what we got. Degrees of freedom are 9. Just a little bit lower than what you would get if you assumed equal variances right here. Degrees of freedom would have been 10. It tells us they're not quite equal. We're being punished slightly from the unequalness that we do see right here. But also it means the confidence interval we give is pretty honest. There was no wild extra assumption about the population. We're trying to see if there's a difference between mu1 and mu2. And there's no reason why these have to be equal as well. They could also be different. The test we're running allows for that difference all at the same time. Just widens our confidence interval a little bit, as seen by dropping degrees of freedom. And now we're on our way. It's 9.14. Let's go 9.1420. Hate rounding with carrying, if I'm being totally honest, but we've got the number down. Any questions at all, folks, with degrees of freedom? Yeah.
Is there a reason why operating the brackets over this?
I think it was only just so that it didn't look weird next to the parentheses. Really just a stylistic choice on that. I think also I decided to do a bracket because I put a bracket on that one as well. I think it's actually why I went bracket this time. Somehow my brain wanted to make it look the same, but really could have been a parenthesis to convey the same thing. Yeah.
So,
Oh, I gotcha. I think that's a good call. Not all problems will necessarily have a test treatment or test group and a control group, but oftentimes, if you do have a treatment group, it's a good idea to put it right there. That is a good thought. When we go to write our confidence interval, it's going to look like this: A less mu1 less mu2 less than B. The A and the B are the things that we're calculating. But mu1 being right there is going to help us interpret this in a nice way. We can go A minus mu2 less mu1 less, that's a plus mu2, B plus mu2. This is essentially the strategy we're going to take. So we're going to put the actual treatment in the middle, do an interpretation on how the treatment changes with respect to the control. So yeah, whether or not it's an experimental design like this, the thing that seems to be like the question in the background should be the very first one, mu1, x bar 1, and so on. Other questions at the moment? Okay, it's a should be mu1, not a must. Your analysis would be accurate if you called trolling the mu2 group. But maybe the best advice to give is try to keep the thing that seems to capture the practical question as mu1. But even if you don't, keep everything consistent all the way down. We never want to switch what mu1 is by accidentally putting in x bar as the different group, x bar 1. That's when we would have the bigger problem. Well, we're ready to calculate the critical number T star. And this is the easy part. Here we breathe a little bit easy. This method is exactly the same as you would have done in chapter 17. Let's review that. We'll share the syntax as well. Say confidence gets 0.95. The degrees of freedom, this is something that you have to calculate on this, but we just did it, 9.1420. If we have the actual raw data, RStudio will calculate this for us automatically, so that's kind of nice. Once we have the degrees of freedom, we just go QT. This is going to spit out our critical number, T star. QT, give to it, 1 minus C divided by 2. We've been using that since chapter 14 when it was a Z star even. Next, import degrees of freedom, lower dot tail equals false. And we've got it. But just for a reminder, change this value for each problem, as well as this part as well. Change this value for each problem, just in case the next problem is maybe 99% confidence, for example. So run this whole syntax. Out comes the critical number, 2.2568. Let's do one really short experiment. What if we did assume equal variances? Degrees of freedom is now 10. It becomes, for a critical number, from 2.25, 2.23 upon rounding. It seems small, 200ths. But remember, the critical number multiplies the standard error, which is large. So this actually can have a big impact. If we assume equal variances, we get a narrower confidence interval. That is only accurate if the variances really are equal. Again, that's another hypothesis test. It's another set of conditions, and those conditions on that test might not be satisfied by the problem in question. A great analysis is one that captures that uncertainty, reduces the number of p-values you're giving to just 1, or interval to just 1. We're going to widen that interval because we're admitting there's no certainty about this. It might be unequal. We're not going to make the assumption they are equal whatsoever. We're just going to run with a larger T star, allowing for that extra uncertainty. So here's the number. It was the larger figure. And here's the syntax above that achieves that. So even though this is an potential exam 3 type of a question, that's the R syntax you would still use because I would give you that critical number in this part right here. And let's just write this out in a way that makes it look more official. T star for that level of confidence is 2.2568. Well, any questions at all, folks, on the T star side? Okay, on to the last bit. We're almost there. The confidence interval itself is pretty fast to calculate because we did all of the hard work. The standard error is not easy. Degrees of freedom is worse. We got our critical number, but we also have to go way back up here, collect even more statistics. Let me also grab this so we don't have to scroll too much as we go to solve that last part. And I think we're ready for the confidence interval. I think we've got all of our information in view. First thing you'd want to do is just write down that formula. It goes x bar 1 minus x bar 2 in blue because that's what estimates mu1 minus mu2. Add or subtract whatever your critical number T star is, and then multiply it by standard error for the difference in those means. Putting this all together finally, recall we have to be pretty careful with this table, but sample mean is this value and that value for the respective groups. So we'll go 2578.0 minus 1880.4. Then add and subtract critical number from right up here, 2.2568. And just about there. Multiply that by standard error, which we calculated carefully down below to get that number, 285.4972. What this finally produces is the difference in means. So now we're ready for the calculator portion. Take all of this information here. Don't know why I deleted that. I don't think we needed it. And I'll do just the computation once I find a spot to park this right over here. So for that first part, go 2578.0 minus 1880.4. Parentheses here could be dropped, but I find I'm more accurate with just interpreting what I'm looking at by associating this first part right here, because it reminds you that's the point estimate for mu1 minus mu2. Then from here, go minus, and then it's the 2.2568 times 285.4972. This gives us our lower bound. So the lower bound is 53 point, let's round to the nearest 10, 53.3 nanograms per gram is less than mu1 minus mu2, those parameters that we specified, which is then less than again. In any good calculator, you should be able to reduplicate this entry. On this one, it's up arrow. Here's where the parentheses help me. There's been times I changed that negative to plus. Not a good thing to do. You want to change this one to plus because you're controlling the thing in the middle there. Parentheses, as silly as it sounds, really helps out the eyes in nailing the right change there. So it's as large or as little as 53.3, as large as 1341.9. Nanograms per gram. So that's our confidence interval. All we now need to do is say what this all means, but look at the way it's subtracted. Mu1 is first, then we're subtracting mu2, and all we got were positive values. This alone is telling us directly we have that mu1 is always larger than our 95% confidence interval. If that's the case, we have statistically significant evidence that mu1 itself is a larger value than mu2. We just have to say all that at once and also say what mu1 and mu2 are at the same time. That's the so-called practical interpretation next. You know what sometimes helps, like we were mentioning before, right up here in the notes, sometimes it does help to isolate one parameter. You're welcome to give an interpretation here, but remember it's supposed to be practical. You're not trying to confuse anyone. So if you told people that the difference between the population mean dopamine in the toluene group minus the control group goes from 53.3 to 1341.9, you might give them a sense of just dizziness. What does that all mean? But if you rephrase everything and target the treatment group, say everything in terms of the treatment group, it's a lot easier to express. And for the people you're trying to give practical information to, it's a lot easier to really process that information. So let's also say an additional and optional step, solve for mu1 right here, 53.3 plus mu2 is less than mu1, which is less than 1341.9 plus mu2. Nanograms per gram, looks like I forgot to state it, so I'll just state it at once. Sorry, just fixing that color coding I forgot about all out of nowhere. So interpreting this statement here is a little bit nicer, I would say. It is up to your option, though. If you interpret here, you still want to talk about mu1 and don't say the difference between the two is from here to here, because it's not necessarily saying in the most direct way that mu1 is actually greater than mu2. In this way, we can say now, keeping our eye right here, and also, before I forget, you'd probably be looking at this part right here, just quick reminders, what was mu1, what was mu2, and we can say finally, we have 95% confidence that, now I want to talk about mu1 to start. The population mean toluene, no, not toluene. Remember, this was about dopamine levels. The toluene was just a treatment. Let's say the population mean dopamine level for rats exposed to toluene. So I've directly addressed mu1 by saying that part right there. Now I want to express the confidence interval. It goes from 53.3 to 1341.9. I'll bring in mu2 after I say that part. Let's say is from 53.3 nanograms per gram larger to, actually, let's just lose that larger. I want to say it at the last part, not in the middle, just to make it flow better, is from that value to 1341.9 nanograms per grams larger than. Now we have to talk about mu2. We'll say larger than the population mean dopamine levels for the rats in the control group. The rats in the control group are really living the life. These are scientific creatures in a certain sense, and they do get a nice treatment, especially if they're in the control group. Maybe not as much for the toluene group, but they are given a very nice treatment up until the point they're in the treatment group. And the reason for that is if you really want this study to work right, you don't want to have the dopamine level being influenced by the upkeep in the cage not being right, the rats being neglected, mistreated. They're actually treated quite nice, all of them, before they enter the experimental design. The control rats still continue to live the easy life. These rats live the hard life. They're furthering science. So that's the ethics side of it that we have to very strongly consider in these kinds of animal studies. But it is important to know that we do that because we want the rats as similar as possible. We want to make a statement about cause and effect. This is a real experimental design. So we can now say down below, if everything is done correctly, if these rats used in the experiment were treated the way they should have been, this study provides significant statistical evidence that toluene causes. That's a dangerous word. We only use the word causes if we know it was really an experimental design, that there was a treatment group and explicitly stated a control group. So the control group in the problem was our indication. We can't say cause and effect language. Without that, we would just say toluene seems to be related to higher dopamine levels, admitting there could be a third unknown confounding variable. Yeah, question here?
So when you don't directly know the cause, could you say there is a correlation?
Yeah, that's a great way to say it as well. A correlation or a relationship, any language along like that would be a great way to go. Sometimes people say there's a correlation, or they might say there's an association between toluene and higher dopamine levels. All of those kinds of words are trying to get away from saying cause and effect if it wasn't experimental design. But here we get to say causes an increase in dopamine Now, we have to add a couple statements, right? These are population averages. So we should say that down here. On average, we're not talking about individual values. We're talking about the average values. And this statement seems like we're saying in humans. It may be true, but that's not what the study was about. They're investigating what happens to rats first as a model, maybe before could we even do human trials on this? Ethics is severe, right? You can't necessarily do the same human trial that you're doing on mice. So here we have to also admit in rats. Even though that might not have been the thrust or the reason for the study, that's what the study was about. Our conclusion has to stay captured in that kind of region. And, oh dear, kind of misanswered that. That was part G. You see if I can fix this. Part G says, does the study provide significant statistical evidence to conclude tolling causes an increase in dopamine levels in rats? Here's that word again. I should have read my own problem before answering that last part, or including this part right here. We're answering this in yes. And the reason we're so sure on that is, look at the confidence interval. It's from 53.3 higher than mu2 to 1341.9 higher than mu2. These values are always positive. If this was negative, however, we would have said no, because there's a chance that mu1 is actually equal to mu2. So down below, just for our explanation, we can make this conclusion because the confidence interval only has positive values. And let's maybe add one other very careful statement here. That's a huge word. We have to be very, very careful when we go to use that word. It is appropriate, and let's make the statement here. We can use cause, effect, language because of the experimental design. We have a true experimental design, in other words, which means there was actually a control group involved in this. And so that's what's allowing the cause and effect language to actually be appropriate here. So lots of things going on with this kind of problem. We'll look into another confidence interval in this lecture notes here. But this is what it would look like if we're doing everything from scratch. Next kind of problem we're going to look at is using RStudio more heavily by importing the data, calling t.test, and making it do that analysis for us. But any questions at the moment? Yeah. Yeah.
Instead of putting in, the problem is just the one side, instead of putting in the spot, putting.
Yeah, that's a great question. I think what I was doing there, but I forgot I was doing it. I think I was having a discussion about equal variances. If we made the assumption of equal, we would add these two, 12, then subtract 2 to get back down to 10. But I forgot to fix the syntax. Thanks for mentioning that. Let me undo that right there. You almost never want to type syntax in Microsoft Word, so I'm trying to fix my environment. There we go. So yeah, this was if we had 10 degrees of freedom. That's assuming equal variances. But I should have fixed the syntax to go back to our degrees of freedom. And it goes to that bigger number right there. Thanks for spotting that. That would have been a terrible one to leave in the notes. If I had a bunch of homework questions where that was used, I couldn't even mark off points. That would have been my error there. Thanks again for spotting it. Other questions so far? Okay. One thing we didn't do on this problem was any condition checking. But you know what is kind of interesting about these problems? Robustness suffers in chapter 17 when there's one population mean. It's actually pretty restricted. Our robustness has very firm guidance on the level of skew, the possibility of outliers, and the sample sizes you're dealing with. However, Interestingly enough, if you're trying to tell apart between parameters, t-dot test is way more robust for several reasons. So here's what's going on with robustness on the t distribution. They're more robust than the one sample methods, especially when you lose symmetry. That's kind of interesting. We're going to look at some data that looks like it should not meet the conditions, but the data I chose specifically for our next problem is one where it does, and it's a big surprise because the data looks bad. The next bullet point here says, when the sizes of the two samples are equal and the two populations being compared have distributions with similar shapes, that's another big one. Probability values for the t-table are accurate even when the sample sizes are as low as 5 for both groups. Similar shapes is something we get more robustness against. Now, what do we mean by this? It's talking about, say, symmetry versus skew. Let's do a really quick table here just to get a feel for what's being conveyed by the author. So this is a good situation, let's say more robust. On the right is a bad situation, not robust at all. I want to give two histograms because we're looking at two independent samples. And for my more robust situation, I'm going to give them similar shapes, which means I'm going to make them both skew to the left. Here's the first one. Something like that. So let's call this sample 1. Next one over here, this one will be sample 2. Similar shape, maybe the skew looks a little different. Something like this, for example. But yeah, it has similar shapes, skew to the left. The size of the sample is important here, but this is nice. We're more robust in this situation because if the shapes are similar, say both skew to the left, the sample mean on this one, X bar, recall from chapter 2, it got pulled to the left in the direction of skew, left skew for this one. But so does this one. Sample mean for this one, wherever it landed, it got pulled to the left as well in the direction of skew, away from the median value. If they go in the same direction, then they are both suffering from the same kind of bias of mismeasuring the center. This is where similar shapes is helpful. But if it looks like this instead, left skew on this one for sample 1, and here's the big problem. Not similar shapes at all. My second sample is right skewed. And now the fact that they're skewed is becoming tremendously bad for us with different shapes. Let's illustrate why by completing this distribution. Here's sample 2. Now what happens in sample 1? X bar gets pulled to the left like we mentioned. Sample 2, well, it's pulled to the right because the skew is in the opposite direction. It's towards the right. X bar goes that way. Let me add some subscripting because we often call them X bar 1, X bar 2. The difference in this second case between the means is artificially wide, wider than it needs to be. The means weren't measuring in the right position in the first place. They're being pulled in opposite directions, making our data look significant when it may not be. The shapes are different. We are losing a whole bunch of robustness, and we are in big trouble unless the sample sizes are very large in the situation. We're more robust when the shapes are similar, skewed in the same direction. Obviously, both symmetric is super ideal, so we're talking about skew. That's because the bias isn't really helping us in any direction. Both of your sample means move in the same direction if the level of skew is similar. So this is the bad case, and this is the explanation of why we get extra robustness simply from similar shapes. The author said something else right here, but I decided to just pop it out as an extra bullet point just to really signify it. Equal sample sizes very greatly improves robustness at the same time as well. Ideally, you want to have something like this. The worst case situation is N1 is 2, N2 is 40. You might fool people saying, look how large our total sample size is, but with this, fairly above anecdotal data. The robustness of our test would suffer massively from just that. But if it looks like this, not ideal, but it's totally fine. We don't lose a lot of robustness if it's unequal like that. It's close to equal, it's not ideal. We're trying to watch out for cases where it's just massively tilted on one sample versus the other, where the scale just goes way in one direction. This one is still pretty even, not so bad. So we have robustness with similar shapes. When we have different shapes like this, we need a pretty large sample size, extra robustness simply by having equal sample sizes. And here's the next best part. So pause right here. The guidance in chapter 17 is doubly used for robustness on this part right here. But this was one sample. We readjust everything that you see right here for these conditions, but we say you have to have independent samples. We're estimating parameters mu1, mu2, sigma 1, sigma 2 are unknown. The sample size for each sample should be at least 5. For the test we're running, that is a requirement, so that's something to look out for. But when we go through the sample size conditions, we're using combined sample sizes. That looks a little bit weird to highlight it that way. We take both samples, add them together. If the combined sample is less than 16, use the T procedures if the data appear close to normal, but the data are skewed. But keep in mind if they're skewed in the same direction, that's a help. This is the harm, skewed in different directions. If they're skewed or outliers are present, do not use T. Skewed in the same direction, you have to use a judgment call. You may, in fact, be able to use this method. If it's at least 16, we have great robustness here, unless there are strong outliers really far from the main pack, or the skewness just looks severe, and large sample sizes, even if we're clearly skewed. Even if we're skewed like this in the wrong directions, if our combined sample sizes are exceeding 40, we do pick up robustness to overcome even that challenge right there. So these 3 bullet points are the same as these 3 bullet points right here. I know there's a 4th one, but these 3 bullet points are the main ones we're looking at. All we're doing is saying N1 plus N2 in place of sample size. So that gives us the robustness for this test. But a full robustness discussion has to also include anything from right here that's extra about our problem. But like before, we don't actually mention everything. For part 1, here, we will just briefly discuss. And it is an important discussion because you saying something about that in this condition is reminding you, yes, I'm really using the right method. It's not something like this, where I should be using a whole different method, paired data, for example. We discuss it briefly because it being simple random samples is not always something that they give us in the abstract. The fact that there is independence is a super detailed discussion that the actual researchers have to give, detailing you how they conducted the study, how they collected the data. Every little bit about that could be relevant to independence. It's not something we can check as outsiders. So again, we briefly discussed this. They may not give you anything at all about independence, but that's okay. We're outsiders looking into a study already conducted. There's only so much we can do. Condition 2, you don't have to mention at all because it's a standing assumption that everything about the population is unknown. The parameters mu1, mu2 should be unknown. We're estimating them. Sigma 1, sigma 2 are definitely unknown as well. So not needed to discuss. In other words, it's just a foregone conclusion that our parameters are unknown. You don't have to say that each and every time. This is the big one. From here, we will carefully discuss and mention N1 plus N2 in your write-up. We need to mention the total sample size, actually say what it is in the problem, because it's guiding you through these bullet points on is robustness working or not. So I need to know that you know what is the combined sample size in the problem so that we can have a really good discussion moving through these parts. So that's it, folks. That's the total robustness conditions for all of these. And when we go to apply this in practice, these data actually look really bad at first. It's kind of interesting. This is a pretty fun problem. We're looking at something called the thematic apperception test. We'll abbreviate that to the TAT. What we have is a group of children and a whole new independent sample of other children with a schizophrenic condition. They're asked to draw pictures. Well, first, they were presented with ambiguous pictures, asked them to tell a story about them, and they were scored in a particular way. The score for this TAT test was the number of stories out of 10, so 10 weird pictures and then 10 corresponding stories that exhibited a positive parent-child relationship. Keep in mind, this is a psychological study. They probably had behavioral experts from child psychology as well. And what's considered a positive parent-child relationship is probably a very, very precise definition, not what we might think as outsiders in psychology, well, me at least, looking in on what's going on. So even though the schizophrenic children don't seem to have as many positive parent-child relationships, it doesn't mean that they were doing anything wrong necessarily. It just means their output was kind of hard to classify as compared to these children over here. They might have been great kids. So that's something to mention right away about this problem. Just because they had the condition of schizophrenia doesn't mean that this particular individual gave 10 weird stories. They just didn't have a way to fit that precise definition from child psychology. So we'll run through this full problem. I'm noticing that we only have about 2 minutes, so we'll make this the problem we come back to after the break, where the major work we do is actually right here. Condition checking is the hardest part about this whole problem. We'll carefully maneuver through the new things about robustness, fit the right spot we're in to see if our data really passes altogether. It looks bad, but it's going to make a pass on this. But it looks like we'll have to wait till we come back after spring break for this problem. Any last questions at all, folks, or comments at the moment? Yeah.
How far is it considered an outlier from the robustness test?
Oh, gotcha. So one thing you can do for these to determine an outlier is throw it into a box plot. That's going to show you the outlier in the 1.5 IQR rule of thumb. And so if you have sample sizes less than 16, an outlier flagged by that rule of thumb is considered large at that point. If an outlier is flagged here, however, keep in mind it's a rule of thumb. And if you're close to 40, maybe combined sample sizes are like 30, maybe 28, at that point you have to make a judgment call. Look at the box plot, how far the outlier looks from the main group, and also look at the histogram at the same time. And that's where we would have to make a judgment call. Does it look far away, both on the box plot and the histogram? Then we have even a problem down here. In fact, that's something we're going to look at with these data. One of them has an outlier, so we need multiple tools to really get a good view of that as well. But other questions at the moment? Okay, well, we'll refresh on all this information here when we come back from the break. Thanks for making it out on today's class, by the way. These classes right before spring break are like the hardest ones to make. But have a relaxing vacation, folks. I know that you also probably have work as well. You may not get spring break on work. But it's a vacation for as far as this class is concerned. And for getting caught up on homework, I am still checking my email. Don't hesitate to write. I'll be happy to work with you. Take care, and I'll see you all when we return on March 31st, I think it is. No, it's April 1st. Sorry about that. I keep forgetting we start on Tuesday.